In this tutorial, we are going to demonstrate how to analyze a simply supported beam. Through this simplified application example, we are going to demonstrate the basic functions of SAP 2000. By completing this tutorial, you will have gained a basic understanding of how to create a finite element model, analyze it, and view the analysis results. Let's get started. The first step is to define the units of the model. In this particular example, we want to express the force using kilonewtons, the distance using meters, and the temperature using Celsius degrees. The units can be selected in the selection box at the lower right corner of the window. Next, we create a new model by selecting the New Model item in the File menu. Alternatively, the New Model item can be selected from the ribbon icons. SAP 2000 has a function for efficiently creating models using standardized templates. These templates create models using some basic parameters entered by the user. Of course, the user can later modify the created models. In the present case, we select the beam template. A new dialog box appears in which we change the number of spans to 1 and the span length to 5. Since we want to model a simply supported beam 5 meters long. On the lower left corner, there is the Restraint checkbox, which is by default selected. When the checkbox is selected, the restraints are also assigned to the model. The Section Properties box allows us to define the section. We leave the default item selected because we are going to modify the section later. We click OK, and the program creates the model. The created model is displayed in two view windows. The left window shows a three-dimensional view, and the right window a view on the XZ plane. In these windows, we can see the location of the global axis X, Y, and Z. We can also see the grid lines. Since we selected the Restraint checkbox in the model template, the program has also assigned the restraints at the two ends. To view the restraints, we hover the cursor on the top of an end node. The program highlights the node in red color. Then we right-click on the node. A new dialog box appears called Object Model Point Information. This gives us information about the selected node. The middle tab is called Assignments, on which we can see the identification of the node. In the present case, it is labeled as 1. Below, we can see a number of other parameters. The parameter in the second line, called Restraint, shows that the translation, denoted as U, is restrained in the 3 local axes 1, 2, and 3, and that the rotation, denoted as R, is restrained about local axes 1 and 3. Next, we need to define the material of the beam. To define the material, we go to the Define menu and select the Materials item. A dialog box named Define Materials appears. In the left box, we can see the list of materials that are automatically created with the model. We select the 4000 PSI model and then select the Modify Show Material button. A new dialog box appears named Material Property Data. In this dialog box, we can see that the material type is concrete. We can also see that the weight per unit volume is 23.5 and the modulus of elasticity is about 24 times 10 to the power of 6. All these values are expressed in the reference units of the model, which are kilonewton and meter. We also define the section of the beam. In the Define menu, we select the section properties and the Frame Sections item. We can see that there is only one item in the properties list, which is the section that was created automatically with the model. To define a new section, we select the Add New Property button. A new dialog box appears with the various options regarding the type of the section. Since we want to define a rectangular concrete section, we select the concrete item in the Frame Section Property Type selection box. We then select the rectangular item in the selection box. A new dialog box appears through which we can define the new rectangular concrete section. On the top text box, we enter the section name, for example, Beam 1. In the dimensions box, we enter a width of 0.2 meters and a depth of 0.5 meters. We also define the material to be 4000 psi by selecting the corresponding item in the material selection box. We press OK to define the section. We can observe that the new section has been added to the properties list. After defining the section, we need to assign it to the element. We click on the beam to select it. The beam then changes from a continuous line to dashed, meaning that it has been selected. We then assign the new section by selecting the Frame Sections item in the Assign menu and the Frame submenu. From the list of sections, we select Beam 1 and click OK. The section has now been assigned. To confirm the section, we right-click on the beam to display the Object Model Line Information dialog box. We can see that the value of the section property is Beam 1. Before assigning the load to the beam, we need to create the load pattern. We select the Load Pattern item in the Define menu. A new dialog box appears, showing the list of the load patterns. We can observe that there is already a load pattern named Dead, which was created with the model. We enter the name Live in the load pattern name and select the item Live in the Type selection box. We leave the self-weight multiplier box as 0. We then click on the Add New Load Pattern button to add the new load pattern to the list. After the creation of the load pattern, we need to create a load case. We select the Load Cases item in the Define menu, which opens a new dialog box. In the dialog box, we can observe that a load case named Live has been created automatically with the creation of the load pattern. We select the Live load case and click on the Modify Show Load Case button. A new dialog box appears. The Loads Applied box shows the load patterns that are added up to form the load case. In this example, the Live load pattern is scaled by a factor of 1. In the load case type, we can observe that this is a static load case, and in the analysis type box that the linear option is selected. In other words, a linear static analysis is carried out for the Live load case. In the next step, we assign the load to the beam. We select the beam by clicking on it. We then go to the Assign menu, the Frame Loads submenu, and then select the distributed item. A new dialog box appears. In the Load Pattern selection box, we select the item Live. In the coordinate system, we select Global. In the load direction, we select Z. In the load type, we select Force. We then enter a value of -10 in the Uniform Load text box. This will assign a uniformly distributed force load on the beam of value 10 kilonewtons per meter in the direction opposite to the global axis Z. Finally, in the options box, we select the Replace Existing Loads. This will replace any loads that may have been previously assigned to the model. Next, we save the model by selecting the Save As item in the File menu. A new dialog box appears asking the path and name of the file. We recommend creating a new folder for each analysis model so that all associated files are grouped together. We now have to set the analysis options. In the Analyze menu, we select the Set Analysis Options item. A dialog box appears, which shows in the available degrees of freedom that all 6 degrees of freedom are available. Next, we select the Set Load Cases to Run item in the Analyze menu. A new dialog box appears showing the list of the load cases. The action column shows whether the load cases will be run when we ask the program to analyze the model. Both the dead and the live load cases are set to run. We run the analysis by clicking the Run Now button. After the analyses are completed, we can observe that the view window displays the deformed shape of the structure. We can also observe that the key lock in the ribbon menu becomes locked. This means that we cannot modify the model any longer, as this would have invalidated the analysis results. The name of the view window is Deformed Shape Dead, which means that the deformed shape displays corresponds to the dead load case. To display the deformed shape for the live load case, we select the Show Deformed Shape icon. And then the case name, we select the live load case. It is also possible to view the bending moment diagram in the beam by selecting the Show Forces icon in the ribbon. We select the Frames item and then select the load case name and the force to be displayed. In this example, we select the live load case and the bending moment about local axis 3. Finally, by right-clicking on the beam, it is possible to view the forces and the displacements at different locations. This concludes the present introduction to SAP 2000.